So, sir, should we start the meeting?
Yes, very good. Very good morning to all. As we are all aware, we have a very important and interesting topic related with dimensional measurement. How to do the measurement in dimensions and to calculate measurement uncertainty. It is a very important topic because dimensional metrology plays a very important role in our daily life. And for the laboratories point of view, for the industries point of view, it is very important. We have with us our extreme speaker, Mr. Mihir
Master.
Abbas. Mihir Abbas Sahab is working right now at MH Technical Services as a director. His master in science in total quality management system, BE in mechanical engineering from JMU, and he is having the diploma from one of the very good reputed institute of Delhi, which is Aryabhat institution. He is a result-oriented professional with over 27 years of rich and extensive experience in quality management system, operation excellence, testing and calibration laboratory accreditation, process improvement, training, auditing, measurement uncertainty evaluation in the field of testing and calibration. His expertise in developing, implementing and maintaining quality management system as per ISO IC 17025 2017 and ISO 9001 and for supporting in BIS certification and other relevant standard specifications. He has worked at Godrej and Weiss Manufacturing Company as Chief Manager, Calibration Services during 2014 to 2022. He has experience in implementation of EFQM, as in 7QC tools, Lean Six Sigma methodologies, etc. He is also certified assessor as per 17025 of NABL. He is a life member of MSI, Metrology Society of India. He is the certified auditor, lead auditor for ISO 9001. He is certified Lean Six Sigma Green Belt. He has provided consultancy for accreditation, certification, etc. and conducted 100 plus audits for 17025 and 9001. He has provided hundreds of trainings on various topics. Even I think he has also provided at our platform many trainings programs. And thank you very much, sir, for accepting our request on this short duration and be enlighten us with your vast knowledge and experience. We have with us our Honorable Shri B. N. Dikshit, sir, Director Legal Metrology. Sir, would you like to speak two words, please?
Yes.
Good morning, sir.
Good morning. So,
Sir, please.
Sri Ashutosh Agrawal ji, Director Legal Metrology, Government of India. Mihir Abbas ji, today expert of the programs. So, the today topic is the measurement of uncertainties in respect of the dimensional measurement. So, earlier when there was no such type of things, there were only the maximum permissible error were there जो है. Later on, when the people went towards the implementation of NABL, as well as the people connected with the NMI, India and as well as the other countries, the concept of the measurement of uncertainty started. In legal metrology, there are the so many hundred of equipments. There the measurement of uncertainty is required, like length measures. So we have the various type of length measures. That is the working standard, secondary standard, reference standards. Apart from that, there are the meter bars, are there the tape measure bars, and tape measures, and scales are there, wooden scales are there. So many things in the legal metrology where the uh, measurement of uncertainty is very important uh, roles used to play जो है. And now everywhere the measurement of uncertainties are become very important even though there is the maximum permissible errors. Maximum the measurement of uncertainty is the 1/3 of the maximum permissible errors. but it sometimes varies from time to time, depending upon its atmosphere and how the standards is having the measurement of uncertainties, and the present standards undertakings is also having the uh, maximum permissible error as well as the measurement of uncertainties, and the certifications from where it has been certified, that is also having the measurement of uncertainties, combining which all the things we are finding out the standard deviation of all the measuring standards uncertainties as a total uncertainty of measurements. So there are the very lot of importance of the measurement of uncertainties. Today, Mr. Abbas will give the nice lecture. I hope that it will be interested for all the industries as well as for the we laboratory peoples. And this lecture will be very nice for the future measurement of this length measures and other type of things. Thank you, Agarwalji. Thank you, Basab and others participant of the program.
Thank you. Thank you very much, sir. We are always thankful to you for your motivating words, which actually keeps us moving. Thank you very much, sir. Now over to you, Mr. Mahir Abbasab. Please, over to you, sir. Please.
Yeah. Good morning to all, and special thanks to Dikshit ji and Ashutosh ji for inviting me and creating this platform. And this is a live platform for a couple of years, and creating a good a platform for the laboratories to gain the knowledge, and which was very essential. And I'm really thankful to especially efforts taken by Ashutosh ji for all this, making this platform alive and correct, and arranging the faculties, experts from all the different fields, and touching all the topic which are important to the society and especially the laboratory fraternity. Okay, thank you once again, and like to start the presentation. Though this is a bit dry subject, and to cover it in just a half an hour or 2 hours, time is a very difficult task for me. I'll try to do that full justice what I can do for on this subject. Okay, so I'm just starting the presentation now. Yeah, the following things I'm going to cover today, it will be starting some definitions, some general recommendation requirements, some key metrology instruments, information about that, and commonly used dimension metrology instruments, and try to cover some basic instrument, micrometer, vernier, and with example of measurement uncertainty calculations and related concepts in in dimension metrology. Now, what I feel, anybody who is in the measurement or in the laboratory or any measurement he is doing, if he understand the concept of measurement, why he is doing the measurement and what is the purpose, what is the significance of measurement, so his measurement will be more valuable to him, more understandable to him. There was a quote given by Sir Lord Kelvin. What he said, to measure is to know. Whenever we do the measure, we want to know something, and when we can measure what we are speaking about and express it in numbers, then we know something about it. If we cannot express it in numbers, it means our knowledge is not satisfactory or not of that quality. It means whatever, if I'm saying I have a fever today, it means that statement is not sufficient. I have to measure the temperature of my body, and then only I can say I have a fever. If the temperature of my body is above the specification limit of the normal temperature of the body, then only we can say it's a fever. So whoever is involved in the measurement must understand this concept of this quotation and imply in their daily life. Whatever they are working, whatever they are there, so they can be, it will be helpful for them. Hope it is clear to all everybody. Now I'm going ahead with that. Yeah. Now, since we are going to touch a topic of measurement uncertainty in dimensional metrology, before that we need to understand what is measurement. I'm just trying to make the two different words, measurement and uncertainty. The measurement is one word, uncertainty is a different word. So we'll go one by one. Measurement. Measurement is basically a process, and process is an activity where we transforms input into output. This is a simple definition. How it is related to us in when in process there is an input, there is a process, and there is output. As simple as that. Now, what could be the important input to the measurement process if we're talking about? What are the key inputs in that? Item to be measured, what we are going to measure. If anybody understand, they can give in the chat box whatever they understand, what could be the input items for the measurement process. Without that, no measurement can be complied or can be successfully completed. For example, the measurement procedure. One should have a procedure, then only he can do the measurement. Then environment conditions. There should be some specified environment conditions required for the measurement and reference to a standard. Anybody who has joined can give me idea which anything else is remaining which required for doing a measurement, whatever they are doing in the laboratory or something, some measurement. Anybody has guessed anything else is remaining? Instrument already covered. Shubham, instrument already covered in that. Okay. Then last thing is the instrument and operator. Okay. Now process. Process basically nothing to carry out the measurement. Now the output. What could be the output of this whole process? Definitely measurement result. But just writing a result or just a simple measurement result, will it be sufficient? I don't think. Measurement result must be reliable and must be accurate. Result with the reliability and accuracy. The values of the uncertainty. These give the significance of the reliability and accuracy. How results less of the uncertainty, better the accurate result is it. And reliability, if laboratory is accredited, competent laboratory have less as less as the CMC, the reliability and the accreditation is there, so it means a reliable result. So measurement result is just not sufficient. It means laboratory has to be accredited, and that accreditation give the significance of reliability. Accuracy, the uncertainty, value of the uncertainty as less as possible. That will give the accuracy of that. Now, further going to the further terms, quantity, it comes under the, whenever we do measurement, there is always results comes in the numbers, the quantity. If we go with the definition of that term, the attributed phenomena, body or substance which can be expressed, I'm talking about the quantity which is measurable. Qualitatively, expressed qualitatively and determined quantitatively. It means when we measure something in terms of the quantity, in terms of numbers, we measure in terms of numbers, but those numbers give the quality of that quantity. That quantity meaning, for example, the we measure the height, length of some object, and there is some prescribed limit, some plus minus limit, tolerance is there. When the numbers we measure of that length in terms of numbers, mm or meter, like that, and gives the quality, tells the quality, because if the within the specification limit, its quality is good, and if this out of the specifications, it's out of that concept. It's a bad quality, like a length, mass, strength, whatever you name it, anything that will be give the quality of the measurable quantity. When we measure something in terms of quantity and give us the quality of that body or something. Now, true value. Whenever we talk about the measurement uncertainty, there is always a term called true value must need to be understood. True value of a quantity or an object. True value. What is the value? True value. The value consistent with the definition of a particular quantity. This value we should understand, know. Then only we can understand the concept of measurement uncertainty. Now, this is a value which can only be determined by a perfect measurement. Perfect measurement means ideal conditions. Temperature 100% stable, humidity 100% stable, the air pressure and other conditions are 100% stable. Under the this should be in such a way which are written in the theoretically. Immediately, all the theoretical concept has to be there. There is no assumption like that. Only, and no measurement is perfect in this world. So what we measure is the mm, whatever the best available resources. For example, there is a bank balance has some limitations, and then only we can know up to the measure the value which is possible up to the bank balance, because true value of a quantity go up to the infinity level. There is a one value of that item. If you measure the weight of your mobile itself or anything, then it can go up to the, there is one weight of that mobile of yours that will go up to the infinity level, actual value, theoretical value. But we cannot go to the that infinity level because of limitations around us, limitation of the equipment available, limitation of the temperature, limitation of the operator. We cannot go up to that level, that precision level, and other related sources. That's why true value we can measure. What we measure, there is some gap in the true value and the value which we measure. So that is the thereby the importance of the measurement necessity lies, because measurement necessity tell us the bandwidth of the true value, that we measure plus value, minus value, and true value might be lying in that range only. That is the significance. I will cover into upcoming slides. So I'll clarify this thing further next level. Now, since we are talking about the metrology, metrology is nothing but the science of calibrating using physical measurement equipment to qualify the physical size of distance from any object. Like I have given the length. Since my topic is the dimension metrology, so I'm covering the dimension metrology means length we are measuring. Length is a measure of distance, size, like that. In international system of quantities, length is a quantity which dimensions distance. In most systems of the measurement, a base unit, it is the base unit for the length is chosen from which all the units are derived. In the international system of units, the base unit for length is the meter or meter, then further divided into mm, kilometer or microns, whatever it may be. It is the base unit is the length, meter for the length. It would be little dry on that subject. It is harsh to say that, but I thought I should define, give you the just indication what is the SI unit for the meter, because we are talking about the length. The as per the definition, it's very difficult to understand. But in simple terms, I can tell you, 1 meter is the length of a path traveled by light in vacuum during a time interval with the duration of 1 by 299,79245 of a second, means speed of light. It is in respect of the speed of light. When the speed of light travel in that particular speed of light travel in that particular duration, that was termed as the 1 meter. The scientists measure, they have some ways to measure all those things. We have limitations to measure all those things, but they have defined it, and we are using that 1 meter up to that level from in our measurements. Further to the terms related to the measurement fraternity is the repeatability, reproducibility. Repeatability means there are 4 conditions basically: the method, observer, instrument, location, and the conditions, and the some short delay or less time delay. If these conditions are same method you are using, same operator, same instrument, same location, same conditions. And conditions mean environment conditions are same, and there is no time gap, then it will be called as the repeatability. If any of these things will change, either operator will change, method will change, or instrument will change, or location and condition will change, or all are same, but there is a gap in the time, then this will call the reproducibility. Accuracy, it's basically degree of closeness of the measurement of result of quantity with respect to the true value, or in other words, the gap between true value and the actual value of the instrument or the measurement. It's a closeness means gap in that way. So the word true value has come up here also. Precision. The precision of a measurement system related to the reproducibility in the same point or like that. If the degree, reproducibility and repeatability combined together maybe comes under precision. It is a degree to which repeated measurements under unchanged conditions show the same results. And least count. The smallest value, the least value one instrument can read is the least count, the error. Basically, nothing but the measured value minus standard value. These are simple forms of this. Now, I have just question to the all the participants who are joined in this training program. Can anybody tell us in the chat box what is the value of repeatability in given below results? Just for I just want to understand how many people are actively participating in this training program. They can give the answer in the chat box. I'll give you the answer. Okay. I have not received any answer. Maybe I'm going ahead with that. Now, repeatability is nothing but the difference between maximum value and minus value. Yeah, this value would be highest value to the difference between highest and lowest value. It is the like this one, 0.004 mm. Now, there are some other conditions of the measurements dimension methodology. Some noise level has to be there. There should not be extra noise. It should be usable. The illumination level should be 250 to 500 lux. Generally, uninterrupted power supply should be there. Ambient conditions for dimension methodology, it is from 20 plus minus 2 to 20 plus minus 0.5 can be possible in the precise measurement to the normal measurements, working level instruments calibrations. And the temperature device, which should be should have a minimum resolution of 0.1 degrees Celsius and humidity at least 1%. These are the kind of things. Now, just for information, I'm giving this where there are the dimension methodology. Some instruments can be calibrated in the permanent facility, some on-site and some mobile. Just try to give you some information over here. The vernier micrometer, this can be done at the permanent facility, mobile also, and on-site also above 1 meter, because it is very difficult to transport. Like this, some information is that which are instrument is technically allowed. This in reference to NABL 129. I'm saying this, and almost the same practice followed across the other ABs also, with some minor changes. This is for the linear basic instruments. If we talk about the further level of instrument, reference instruments in just like gauge block comparators, these are possible at permanent facility as well as site also this way for reference instruments. And the linear measurements, some other instruments are also given over there, like surface plates. These are possible at permanent site. Mobile, it is only if the person is using for in their mobile facility, that is also possible. And caliper checkers, have height gauge, everything there. And what are the parameters required to be calibrated in terms of vernier caliper? What are the parameter what maximum can be calibrated, like error in external jaws, error in internal jaws, error in depth, these are Indian standards has been given over there, because I'm in India and we mainly follows the Indian standards. If they want to follow some international standards, they can follow somewhat international standard as well. Yes. For dial indicator like 11498 and dial indicator plunger type 2092, like that, there are standards there. And what other things needs to be calibrated, what are the recommended masters could be there. All metrology people must know all those things. Yeah, further to this micrometer, depth micrometer, like that, just like in system micrometer 2967, I guess is there. What we measure the error of measurement in the screw error, we sometimes call it screw error as well. Flatness of anvils, parallelism of anvils, like that. And vernier height gauge, we measure the height working length of parallelism of subscriber to base. Sometimes we do the calibration squareness of movement of the base only in case of 2D and electronic height gauge also. Like that, we do that. Gauge blocks, we do the calibration for gauge length, variation in length, and flatness, like that. For different grades, which master needs to be used as a reference for K can be calibrated with the K only. Zero grade for zero grade gauge calibrations, K grade is required, like that. This some information is available. I'm just sharing it to you for your knowledge purpose. For caliper checker calibration, is step gauge or gauge block with CMM surface. These are the common instruments which can be used. Now, I'm just going ahead with some basic information sharing, just for understanding purpose. Okay, these are the instruments which are commonly used in the industry, just like micrometers. Basically, there are three types of micrometers in broad category: outside, inside, and depth micrometer. And what are the parameters there in that way? External micrometer is basically used for the weights and length measurement outside, outside external measurements only. For inside micrometer used for the inside holes or bores measurement only, and depth micrometer used for the depth or holes and grooves measurement purpose. And when we talk about the vernier caliper, there are generally three categories are there. Vernier caliper with having mechanical type, sometimes we call, and it has a vernier scale. Digital calipers, digital indication is there, and dial type calipers. There are three categories of available. I'm going to cover the depth of the vernier caliper, one example of the dimension methodology with uncertainty calculations, everything for the vernier caliper only. I'm just going ahead with the more details for depth gauges. Depth depth bar is there, which is used to, if you can see in the picture, the how we use it. An external charge for the external measurement, maybe round object or any. I've shown an example of round object. It can be used for the round object, and the square object or any shape of the object. It can be there. It can be used for the external measurement. For internal measurement, generally the gaps and the IDs or internal diameters, like that, on some other gaps, it can be used for internal measurement. Now, if we talk about the vernier caliper, it has what are the parts? It has some outside jaws, some sliding jaws, some inside jaws, and locking screw, and main scale, and depth bar, depth gauge or depth bar we used to call it. Then how we use it? It can measure down. Normally, mechanical type vernier caliper has least count is 0.002 mm. The best available. It can be coarser to that also, but the best available is 0.002 mm in case of mechanical type of vernier caliper. Now, when how to understand, I'm just, because sometimes people are unable to read the reading from that, I'm just trying to cover that aspect as well. When we do the measurement, we need to check it from the is there any gap in that there should light is passing over there. If the gap is there, once we close it completely, it means there is some initial error in the vernier. So we should not use those kind of vernier, or either we get it repaired, or we need to consider that error also in our reading, so that we can get only the correct reading. And once we take the measurements for actual measurement, once the instrument is okay, then we should yeah, if we can close the lock the slide bar also, and close the that screw, so that it can be stable on that thing. There should not be doubt on the readings which we are going to take. Now, I'm just giving an example. If how to read the vernier caliper. It has a main scale and the vernier scale. The red color readings are written in the 16 whole mm, like this. Like here, these are the readings. This is the main scale. The reading 16 whole is there. Then the vernier scale is there. How to take the reading is the vernier scale, which line is exactly matching with the main scale reading. If this line is matching, means it is 0.38. here this point, this 1 means 0.1, this is 0.2, 0.3 and 0.4. Below that 0.4, 0.38. Each reading is, each division of this is scale, vernier scale is 0.02 mm. So this is how the readings are taken like this. If you see the just enlarged image of a 16 plus 0 is coming more than 16, and if you see there is no line is perfectly matching, this line is matching just before the before 4. So 4 is means 0.040, and before that one reading, one division is equal to 0.02. So 0.02 minus 4.4 this way, 16 whole and 0.38 on the vernier scale, then the 6.38. This is how the readings are taken on the vernier, this mechanical type vernier. Now, reading dial type calipers, how we read here, we can adjust it also when the this slides are matching, jaws are matching, we can adjust here also. But it should be ideally in the 12 o'clock position, 0 should be there generally in for correct feed, correct working of the instrument. Now, digital calipers, here we can, when jaws are matching, jaws are exactly matching, there is no light on this. We can set a 0, it will come 0, and we can switch on this instrument and 0 can be set it over there, and reading can be taken. Once we set the reading, we can tighten this screw and stop there and remove the object and check the reading over there. This can also be done here also. Now, in India, there are the different Indian standards available for the readings of the vernier calipers. So just I'm giving an idea what are the reference standard we use. I'm trying to cover the example of in measurement uncertainty where I'm using the slip gauge set of 0 grade from 0.5 to 100 and 125 to 500 and slip gauge accessories also in this category, and unknown conditions 20 plus minus 2 we can use, or this we can use for this measurement. Now, calibration procedure, how the calibration is being done. We should cover the minimum 5 points, or maximum we can take 10 or 20 points, depends on the laboratory nature of work and the as per requirement of the customer. I'm trying to cover here, these are the points we have taken. Some for the range of the vernier is 300 mm and 0, 31.2 and 61.4, like this, these readings we have taken here. And depth measurement is also done. We have to do 0 error for the depth measurement, and maximum reading we can take up to the 10, 5, 3, or the average of we can consider for the reporting to the customer for other reading points. And sometimes in some point we need to ring the slip gauges together to take the value of the in between different ranges. And this is how we need to make a plus, clean the slip gauges properly, and then we need to hold it cross, just plus, make a plus sign, then rotate it like that. One should be either one in different directions, so that they can ring, and all the vacuum will be created, all the air will be released from there, and this way, and once it will be in the same position in the opposite direction, we have to move it and finish back, it will be the ring properly. This is how the use of the slip gauges by ringing. Now, vernier caliper error, there we have to check the error once we do the calibration or measurement for the vernier caliper. First, 0 error by checking the light in the once we match the jaws over there all together, try to make it 0. Let's see if it is coming 0 in case of vernier caliper or dial or digital, whatever may be, and there should not be any light. When we check in the towards the light, there should not be any gap or light visible between the external jaws and internal jaws. If there is some light is there, it means there is some gap over there. Now, once it is okay, then respective size of the slip gauge can be placed either if with large size place you can place on the surface plate, or it can be in your hand and you can measure it with that. Or caliper checker, you can also use it, or you can fix in the slip gauge accessories the specific size of the slip gauges, so that you can take the reading properly and take the reading properly without putting any extra forces. This should be if you see the standard, each sometimes that get 10 Newton, more than 10 Newton force should not be applied, but we cannot measure. So you have to put the some slight pressure using your thumb, so that it should not be too much of the pressure. It should not be uh, limited pressure, so that you can have a feel. If you have the experience, then definitely you can have a feel. Check the reading of the caliper and zero setting, and take the reading properly, and repeat this procedure on across all the points. Same point and the same way you have to do it. For internal measurement, follow this with all slip gauges has been put into the accessories, and take the reading of the internal. Some scribble, some slip gauge accessories, you know how to use it. These accessories fit the slip gauges and take the internal measurements over there. In combined width, if you want to use it combined width initial value, you can use a micrometer also, and to check the what is the combined width of the internal jaws, in that way initial value at the time of calibration. Now for the parallelism of the jaws, especially the external jaws I'm talking about, or maybe you can use it for internal jaws as well. Slip gauges of a specific size with the range of the caliper should be top, middle, and end. In the three points, you can take the reading. It means the size of the slip gauge of size is like that jaws. Then here, I'll just tell you. These are the jaws of here. You can place the slip gauge here, here, and here. When you talk about the internal, create a gap over here, the here and here, like that. If there is a difference is coming out, when you take the reading over here, slip gauge, take the reading here and take the reading here. If there is a difference between this reading to this reading, then there is a issue of the parallelism of the jaws. That difference in reading is basically the parallelism of the jaws. So this way you can take the values of the parallelism as well for the your your vernier caliper jaws also. Now depth measurement. Check the zero error by joining the jaws of the caliper directly. Set to it zero. Once you set it zero in the reference surface plate or some slip value, and take the reading and put it into the make a gap of that, and do slider down 1 or 2 mm, or maybe the reading wherever you want to take, with creating the gap with the slip gauges and slip gauge accessories, or maybe you can use directly the caliper checker also, and vertically down this way, like this. Here, like this. Here, then you can make a bridge of the some gap, put a slip gauge over here, put a slip gauge over here, like that, and there will be the surface plate, or maybe put another slip gauge, so that you can take the readings of the whatever the reading you want to take for the depth gauges. Like you can do the depth measurement this way also. So this is how the internal, external measurements and depth measurement can be done. It depends upon the size or the readings what you want to take as per the calibration procedure or SOP of your lab. You can do the measurement like that. Now I'm going to go ahead with the typical some example of the measurement uncertainty for a vernier caliper. Now, before going to start the measurement uncertainty concept, I like to tell you there is a difference between error and uncertainty. One need to understand those are involved in the basic calibration basic calibration measurements, or in calibration. Those are working the calibration laboratories. They need to understand, or testing laboratory, or anything associated with the measurement. They need to understand the error and uncertainty. Both are different. aspects. Sometimes people mix it, error and uncertainty, or they mix this together, and that is not the correct, because error is the property of the instrument and uncertainty is the property of the measurement. And in measurement, instrument is one of the part, but that is not all, because it has many other components in uncertainty. But instrument is one of the part. It has many other components, even the operator, even the unknown conditions, method which you are going to use it. It has many other things, many other factors are there. That is one thing. Error, in nutshell, if we in the technical terms we say error is the difference between the true value and the measured result. Whatever the result you measure and the true value of that object, which actually goes up to the infinity level, is the difference, is the error. But uncertainty is the basically a dispersion. Dispersion means the bikhrav, the fallout of the of some values which are attributed to the measurement, which give us the true values lying between that range. I'll just cover in the coming slide. It will more that will give more clarity to you. Error is the basically instrument property, and this result. Error generally is single value. Error may be in plus, error may be in minus, like that, or in terms of percentage, but it would be either in the plus or minus. But uncertainty is a range, plus and minus. It cannot be considered as the one plus uncertainty or minus uncertainty. No, it's a plus minus same value. Many times error can be applied as a correction to a result. For example, when we use it in temperature or something, some other fields, in mass also, then we many times times error can be applied correction to a result in temperature or some other fields. We consider the plus error, minus error to correct the result, to consider the actual value. But uncertainty cannot be applied to correct a result. It is there, it will remain in the result. It cannot be applied as a correction factor. Error may be plus or minus, but uncertainty is a non-negative value. It will be plus and minus both. It's a non-negative. It will go up to the range like that. Now, if the definition of the measurement uncertainty given by the ISO is, I'll like to tell you that uncertainty measurement is a parameter associated with the result of a measurement, and that characterizes the dispersion of the true values, which could reasonably be attributed to the measurement. In simple terms, if I'll say, the uncertainty measurement is a parameter. It's a parameter. Just like for any object, any chemical, it has some chemical properties. So, chemical properties, it has some steel, it has a mechanical properties. Similarly, the it's a parameter uncertainty. It's a parameter related to associate with the result of a measurement. It's a measurement का characteristics है, जैसे technical characteristics होती है, IT characteristics होती है, chemical characteristics हो सकती है, किसी भी चीज की when we consider the chemical aspects से. Similarly, for measurement result, it is a parameter, उसका characteristics है. That characteristics define the dispersion of the true values. It means true value का एक dispersion, एक बिखराव, एक फैलाव बताता है, which could reasonably be attributed to the measurement. एक जो measurement है हमारा, जो हम measure कर रहे हैं, for example, we are measuring a length using the vernier caliper. So length, that vernier caliper is our measurement, जिसका हम values measure कर रहे हैं, उसको calibrate कर रहे हैं using the slip gauge. That true value of the actual measurement of this vernier caliper is lying between some ranges like that. That would be the explanation. Or if still there is some doubt about that, it will be clear in this slide. I'll just try to tell you some this example. There is some measurement result. For example, the 100 mm slip we are using, and we are measuring the 100 mm on the vernier caliper. Results are 0, 0. Means 100 mm of slip, it is giving the 100 mm reading on the vernier caliper, right? And but it has some uncertainty. When we calculate the uncertainty is coming out considering all the related component and factors like that, is coming out 0.012 mm. Then true value, the results are there is no error in the vernier caliper at 100 mm, but uncertainty is this. So this is the dispersion plus uncertainty, that is here I have given the plus minus 0.012 mm plus 0.012 mm means 100.012. This is the plus, this is the minus 99.88. It means true value is lying somewhere in between of the vernier caliper. True value lying somewhere in between, but where we don't know. That too at a 95% probability. It means if I'll repeat those results, 100 results with that same slip, and on the vernier for the same value 100 times, then there is a probability that 95 readings will come in this range of mine, 100.012 to 99.88, and 5% there is a probability will go outside of this. This is the meaning of the confidence level of 95% or probability of 95%. Hope this is clear now. Now, how these values are being calculated, that's what I'm going to cover in the upcoming slides. Yeah. All your questions will be answered later this stage. Once I'll complete the slides, then only your questions will be answered. Now, how to calculate measurement uncertainty for a length measurement? Mr. Kiran, if you can't see the slides, please check internet connections. If hope others can see my slides.
Yes, sir. Yes, sir. It is very well clear. Please continue, and we will take the questions as you have already informed at the end of the program. Please.
Okay. Okay. Okay.
Thank you.
Okay. Thank you. Okay. Now, how to calculate the measurement uncertainty for dimensional metrology? One example, I'm just trying to cover it. There are two types of estimations or evaluation in the this measurement uncertainty. Now, here word has been used to evaluate, not to calculate. There is a difference between evaluate and calculate. Calculate means when we have a formula, suppose A equal to some value, B equal to some value, C equal to some value, and A plus B equal to C, like that. That is called calculations. But when we have certain assumptions to apply, certain concept is only given, then we have to apply our mind, apply our judgment. Then the term will be used as to evaluate. It means we have to apply as per our conditions. Whatever the conditions are available in our laboratory, in our specific measurement, then this term is used as a evaluate. Hope it is clear. That's why it is different for different. The concept is same. Uncertainty values are coming different for different labs because you are evaluating as per your conditions. Now, type A uncertainty components basically in type A mainly some statistical tools are being used. Sometimes it is called as the statistical uncertainty calculations are usually taken from the repeatable measurements in terms of dimensional metrology, if I talk about precisely. Now, type B. Normally, type A, it can be controlled a bit because if you have a skill, you try to minimize it. To large extent, it may be zero also. If you have 100% repeatability, it may be zero also in your case. But type B is the systematic components which cannot be zero. Under any circumstances, it will be some values. However, you can try to minimize it as much as possible. Certain components you can try to minimize it. For example, the temperature will come out into that. So if you control the temperature as much as possible, You could minimize to point instead of 2 degree plus minus temperature, you can maintain it 0.5. It will be less in a value of the uncertainty, but you cannot make it 0 because these are the part of the system related things. Here the mainly things come out the type B evaluation uncertainty calibration from the certificates, accuracies of the instrument, least count, etc. will come into that because it cannot be eliminated. Accuracy of the instrument cannot be eliminated. There is sometimes we call this type A is the random and type B systematic. But in certain cases, it may not be 100% true. But in dimensions, it seems to be true. Type A is random because of the random characteristics of the instrument, the static repeatability. It's a random. It's not a fixed thing. It can vary. It may be 0, it may be high value also. But systematic type B means system. It is part of the system. For example, calibration uncertainty of the master instruments, accuracy of the master instruments, least count of the UC. These are the systematic. You cannot eliminate it. And they are the bare minimum. When we consider calculate the uncertainty or try to estimate it, then there are certain aspects we need to consider or we should know before going ahead with that. They are the probability distributions. In probability distribution, our first choice is to have the normal use the normal distributions. Normal distribution, when to use, there are certain conditions, then only in those conditions only we can use the normal distributions. Wait a minute. Yeah. Normal distribution, they are the conditions when quoted uncertainty a component is stated along with the level of confidence. In such cases, one has to find out the value of coverage factor so that the quoted uncertainty component divided by the coverage factor to obtain the value of the standard uncertainty. Example, major uncertainty quoted in the calibration certificate of equipment. Master instruments calibration certificate में whatever the uncertainty is quoted here, we need to consider the normal distribution because those are given with some level of confidence and stated with the K factor. That's why we need to use the normal distribution for the all the uncertainty quoted with the in the calibration certificates. Yeah. Now, second choice is to use the rectangular distribution. And what is the condition for that? When quoted uncertainty is not stated along with the level of confidence, then only we have to use the level of this consider this rectangle as a full value. In such cases, we have to define it divided with the root 3 to obtain the value of the standard uncertainty. Example, accuracy of the equipment, least count of the UC, like that. In such cases, we have to use it the rectangular distribution. And the first case is the normal distribution. I'm coming back to normal distribution. When uncertainty component, for example, the calibration certificate, uncertainty of the master defined in its calibration certificate. In that case, we have to consider normal distributions. In this case, we have to divide the uncertainty with the K factor and K factor to get the standard uncertainty component for the calculation for the estimation of the uncertainty. And when the confidence level is not defined, in that case, we have to consider the rectangular distributions in case just like a accuracy or least count of the accuracy of the master equipment and least count of the UAC, like that. Now, confidence level. Now, and confidence level as the accreditation process is of the laboratories, it is fixed. All laboratory has to report at the 95%. But in certain research level laboratories, high precision laboratories, earlier NPL used to define the 99.7 also. But nowadays the things internationally is fixed as a 95 or 95.45. These terms will be used worldwide. So all laboratories are giving the confidence level as either 95 or exactly 95, then they are using the coverage factor 1.96, or if they are writing as approximately 95, it means they are using the 95.45% confidence level and coverage factor k equal to 2, like that. It can go to the up to the 3 maximum 99.7, like that. It will go in that way. Basically, the purpose of this is the when you may uh, I'm just trying to tell you the interpretation of this in simple terms. If you, for example, the already I have given an example of 100 mm at 100 mm reading, your error is 0, but uncertainty value is 0.012 mm. In that case, if you repeat those measurements 100 times, 95% times your result will be within the same range, for confidence level is 95, and 5% chance or 5 readings may lie outside of that range of 0 plus minus 0.012. This is the meaning of that confidence level. Hope it is clear to all. Now, after the measurement, there is always a doubt about the measurement or a result. That doubt is the measurement uncertainty. For example, how what is the distance I'm traveling from my home to office, like that? Maybe 5 kilometer, exactly 5 kilometer? No, plus minus something, maybe 4.5 or 5.5, like that. That doubt is the basically the uncertainty. And similarly, the time taken from my home to office, if for example, generally I'm taking 30 minutes, but not exactly the 30 minutes. There are sometimes I may reach 25 minutes, sometimes it may go to 35 minutes, it may go to 40 minutes. There are certain factors in which in maybe the timing, at what time I am going, the traffic conditions, my vehicle conditions, and what speed I am going, like that. These are the factors affecting the actual time taken to the reaching to the office. Those factors which are some predictable, some unpredictable, comes under the uncertainty. Those creating the doubt at what time I can reach. That doubt is nothing but the uncertainty of the measurement. And why we evaluate it? Why? What is the purpose of calculating uncertainty? I'll cover the example. I'm just telling the significance of calculating the measurement uncertainty of a result. Earlier, I have explained you what definition of the true value. True value of something is the fixed value which give the indication, which measure in terms of quantity and tells us the quality of that object or that process or something, that object. So similarly, measurement uncertainty of a result is a quantitative indication of its quality. When we are measuring some result, measuring something, so it gives us the quality, tells us the quality of that measurement. In terms of, or in other words, we can say it is the degree of doubtness. Lesser the doubt, greater the quality. Means the how much value of my result is there. For example, 100 mm I have measured on the vernier caliper or calibrated the vernier with slip gauges 100 mm. Though my error is 0, 100 standard value, 100 measured value are exactly matching. No error. But the less my answer, if my uncertainty is 0.012 mm, 12 microns, and another lab is having the uncertainty 0. Maybe 0.1 mm, 0.1 mm. It means they have a large doubt of their result. Lesser the doubt, greater the quality. That is the meaning of the uncertainty values. That's why if you see, the good labs are having the small value of these CMCs, calibration measurement capability. CMC is nothing but the best value of their uncertainty. Now, why uncertainty is required? It can be used for the improvement of our measurement procedure, test procedure. If we come to know we calculate evaluate the measurement uncertainty for our measurement, we come to know, then it's a value doubt is coming out more. Then we try to improve our procedure. We can try to proceed maybe some repeatability, or maybe we can change our master also. Master is not giving the correct reading or repeatable readings. We try to improve that also. We proceed, we control the temperature, ambient condition of the laboratory. That also be possible. Even the training of the employee also possible by after evaluating it. If somebody is not giving the correct repeatable results, we can train the people also. This will give the overall improvement in our procedure or system of the laboratory. It also allows us to obtain valid measurement results which are widely acceptable. If our laboratory is accredited and we are giving the value of the uncertainty also, results are acceptable everywhere. So more valid and more confidence will be there in giving the results to the customer, against the customer, or against to the customer, or any legal requirement would be there. It will be useful for everywhere throughout the world. Sources of uncertainty. What could be the sources of uncertainty? If we are talking about the UEC or measurement, its range, it's the least count. These are the main thing. For example, I am considering the vernier caliper of 300 mm. Least count is suppose 0.02 mm. These are the components from there. And other sources, environmental conditions, temperature, humidity would be the part of this. What is the temperature, atmospheric pressure could be there. These are related to this. If talking about the dimensions, temperature would be the main aspect. Sir, Mr. Taking the readings either in the vernier caliper of mechanical type or some volume measurement or some other measurement where he has to use his eyes correctly in the same label correctly, then the parallax error is there. And computational error, some calculations would be there. So it would be computational error may be there. These are the impact of the effect of the personnel or operator. Some other instrumental effect would be there. So Shankarji, questions will be taken at the end only. Instrumental effect, master instrument, I'm talking about the accuracy of the master instruments, measurement uncertainty in its calibration, readability of any instrument. Readability, if we are using the as a master, the readability of the master is also become the one of the component. For example, I'm considering the vernier caliper up to 300 mm, and non conditions considered is plus minus 22 plus minus 1 here we have considered, and parameter to be calibrated error in the external jaws. For example, the 10 readings are taken like this for the measurement uncertainty calibration data. These are the readings and some variation is there. And how we have taken the average will be calculated like this. The formula is also given. We have to add all these values and divide by the number of reading, that is 10, and this will give the average like this. Now we have to calculate the standard deviation. The standard deviation formula is given over there. Now Excel, you can calculate through Excel also. Basically nothing but the difference between the average of this average. This value x1 means xi means this value minus this, then square of this. this value, then average, this will give the x2 like that. There will be 10 values. All 10 values, the square of the 10 values will be some over here, and n minus 1. This is the simple standard deviation formula, and standard deviation value is also calculated over here just for an example of yours. Now, for example, these are the total values as been this reading well or taken standard values, and these are the readings of the external jaws are taken and the internal jaws are taken, and this way we have taken the results. For example, 31.12 like that, an average of the 3 readings, minimum 3 readings you can take on the all points, but uncertainty value, you where you want to calculate the uncertainty, it can be more, maybe 5 minimum or 10 readings you can take. So here I have the example taken the 10 readings over there. This average of 3 readings can be taken to report in the calibration certificate or calibration results. They are the test readings taken 3 on external and internal, and average which needs to be reported in the calibration certificate. Like this is could be taken over there. For calculations of the type A error or type A uncertainty, standard deviation divided by n and then square root of the value. This will be the type A value. So we have, because the value is so small, so we have considered into microns this way. And degree of freedom for type A is 10 minus 1, n minus 1, as per the worldwide enable guidelines are available. So degree of freedom is taken as a 9. Number of readings minus 1. This way we have to do. And type B. Now type B, I'm going to explain each and every component one by one. Uncertainty due to the master instruments calibration certificate taken from the calibration certificate to master. We have considered the two masters over here. I've already told you, slip gauge accessories and the slip gauge set. Here the data should be taken from their calibration certificate, master or traceability certificate, sometimes it's called it. There are two ways we can combine together them and take up the RMS value, or individual we can do. Both ways we can do. So I have taken here the RMS value approach over here. So I'm consider the values 0.8 microns is for the accessories and 0.11 for the slip gauge set. So both values have been taken the square of that values, and square root then divided by 2 is the 0.40838 is the combined impact of the masters in the uncertainty of the total measurements. And degree of freedom is in type B components, individual component is the infinity always. And this is all these values are given in the uncertainty guidelines. The procedure I'm explaining you for all these aspects. Now another is the accuracy. This accuracy of the we have taken some values here. The accuracy of the accessory defined by the manufacturer is 0.9 microns, and similarly for the slip gauge also 0.29 like that we have taken, and the here we have considered the normal distribution, that's why it is divided by √3. And the combined effect we calculated from these values is 0.5459 micron is coming out, and degree of freedom is 0. Sorry, infinity. Master, I'm again repeating, the masters we consider the slip gauge accessories and the slip gauges, and the two masters, the cumulative factor of the accuracy we have considered here. And slip gauge accessories, the accuracy is 0.9, and the slip gauge gauge blocks or slip gauges is 0.29, and both the values RMS value has been considered, and the √3 is considered the dividing factor, as we have considered the rectangular distributions over here. That I already explained you why we are considering the rectangular distribution, because there is no confidence level defined here. Now, uncertainty value due to the resolution of the UUC. Here, I have considered the resolution of the UUC 0.01, and then it will be given and considering the 25% of that way that value. So 25% of that value is 0.0. That's why given is the divide by 4 is there. And to convert into the microns is the multiplication is done for with 1000 and divide by root 3, considering the rectangular distribution. This is how the calculation is coming. I'm explaining again. Here resolution of the UC we are considering as the resolution of the UC is 0.01 mm we have considered, and the 25% of the here because this was analog dial type, you can say dial type or vernier we have considered over here. The 25% of the least count component we have considered, and to convert into the microns, 1000 multiplication has been done with the 1000, and root 3 dividing factor considered as it is no confidence level is defined for this. It's considered the rectangular distributions. The value is coming out 0.058 microns per meter. And degree of freedom is again here's the infinity for the type B individual components. Now other components are there here. The mainly the components are coming out with the just now here the components are coming out mainly because of the thermal coefficient of expansion of the different materials used in the because in thermal metrology or length measurement, if something is used beyond the temperature of the reference temperature, it will expand or contract. So that thing also we have considered to give the confidence in the measurement result. Here soaking temperature difference we have considered the 0.2 here difference. Base temperature is 20 degree, limit plus minus 1 we have considered. The start temperature was 20.4 and end temperature was 20.2. The difference is 0.2. If you see the difference is coming out a delta T, the difference 0.2 temperature. And UC, the thermal coefficient of expansion of UC we have considered is 11.5 into 10 power minus 6, or in terms of the four zeros and 115. Slip gauge access is also same, because the material is SS, and slip gauge set maybe we have considered the tungsten carbide slip gauges over here. Its value is 4.7 into 10 power minus 6. The difference is coming out here. The from the slip gauge to the UEC is 6.8 into 10 power minus 6, or 5 times 0 into 6.8, and the difference is that the average is coming out. Average value is also written over there. Here because soaking temperature is there, so we have considered the average of what, this value UC, slip gauge axis, and this, all these three values average is coming out 92. Average of UC, slip gauge accessories, and slip gauge, all these three together, average of this. Because of cumulative factor, please switch off your mic. It's creating a disturbance, please. Ashutoshi, can you please switch off their mic? Yeah, and this is the average value, and the UC range is 300. Then it should be converted into the microns. That's why this value is coming out 1000 over here. And all these values are considered in the rectangular distribution divided by root 3. And the total calculations will be coming out like that, 0.3199. Degree freedom is also infinity for this component. Now, just to explain the thermal coefficient of expansion of any material, basically it is nothing but the change in length with respect to the change in temperature. Length will change with respect, if temperature increases it will expand, if temperature decreases it will contract. This is the simple meaning of that. Here we have considered thermal coefficient expansion for typical vernier caliper usually made of steel is around 11.5 10 power minus 6 per degree Celsius. Meaning for every degree Celsius temperature increase in temperature, the length of the caliper will expand by very small amount, approximately 11.5 million, or that is 10 power minus 6 of its original length. So this is how we have considered the thermal coefficient expansion. And this Ashutoshi, there is some.
Yeah, all are requested to kindly switch off your mic, please. Atulji, RSL Ahmedabad, kindly switch off their mic. Okay, please continue, sir.
Yeah. So thermal coefficient expansion is a very, though value may be very minimal or not significant, but all the people are working in the dimensional metrology must know all these things. I hope definitely people might be knowing. I'm just trying to explain it here, just to refresh them. The another component is the uncertainty to the difference between coefficient of thermal expansion of material of the master and UC. If there is some understand, that's what deliberately I have considered the sleepiest set of the tungsten carbide. Having the value is of thermal coefficient is different than the UC. So that you can understand that. Here we can consider the temperature limit plus minus 1 in initially we have given 20 plus minus 1, so we have considered this 20 plus minus 1 value, then this will be given over here, so that is considered as a 1, and the difference of this slip gauge set thermal coefficient expansion and the UC that is considered over here, and again length is 300 to 1000 multiplied with to convert into the microns. This is how the calculation is coming out. Because of the value of the difference of thermal coefficient of expansion of the master and EUC, the value of the uncertainty, systematic uncertainty component is 1.17 micron at 300 mm length, 300 length of the vernier caliper. Yeah. Now, uncertainty due to the temperature monitoring device, TMD, whatever the temperature monitoring device we are using in the lab for the measurement of temperature, then that difference uncertainty is also can be used, the accuracy and uncertainty both can be used over there, and the difference of the thermal coefficient of expansion that we have already calculated, then maximum range of the vernier 300 into 1000, again this value is coming out in 0.1666 microns, and degree of freedom is definitely the infinity. So this also we go to up to the sixth component. Now calculation of the combined uncertainty. There are ways of the calculation of the combined uncertainty. RMS value we can do type A square. The formula is type A uncertainty, then square of this and the square root. Type B uncertainty and then square of this and the under. As we want to calculate the cumulative effect. For calculating the cumulative effect, this approach is the best approach because it will definitely gives little higher value in from the one component to other. Here UA1 we have to, then UB1, UB2, then we go to up to UB6. All these values are given over here. The one UA1 value, UB1, UB2, UB3, UB4, UB5, and UB6. And cumulative effect is combined uncertainty is 6.0259 microns, like that. Now, a step to calculate the effective degree of freedom. Now, the formula for calculation of the effective degree of freedom for the combined uncertainty, UC power 4 of the UC. This is the UC value combined uncertainty. It's power 4. Then divided by UA power 4 divided by the degree of freedom. It was 10 minus 1, 9. And all others are the infinity. UB1, UB2, UB3, UB4, UB5, UB6. So once the value is divided by the infinity, all these values will become the 0. Then all the remaining values will be there, UC power 4 and UA power 4 divided by 9. So this will become the 0 and this value will come out in millions and billions like that. Is if this value is greater than 30, effective degree of freedom, then we can consider the value of degree of freedom is overall the infinity. Is I'm repeating again, when effective degree of freedom calculations come out with from this formula, is value is greater than 30, then we have to consider it is the infinity, because as per the NABL guidelines over here, in some 10 guidance it may be like that, the 50 also overseas guideline here, when degree of freedom is greater than 30, here if we see effective degree of freedom, if value is coming out less, then we have to consider the K factor from this table like that. Since value is coming out 30, it means considered as the infinity. When it is considered as the infinity, if we are using this approximately 95 or 95.45 confidence level, then this our K factor will be 2. This is how the calculation is. If for example our value of the year in maybe because of some other components, if UA value would be more, it depends upon the use, this all result is depend upon the value of the UA and UC. UA any type A uncertainty and UC combined uncertainty. If UA is the major contributing factor in type in UC combined uncertainty, then this value may be a little low. For example, if this value would have been the 10, I'm just taking an example so for your understanding, if that value would be the 10, degree freedom value would be 10, in that case 2.28 would be your K factor in the certificate. You can check the master's your calibration certificate of your master whether the lab has defined the K factor is the 2 or 1.96. If they have defined 1.96 or 2, it means their effective degree freedom value would be more than 30, and they have considered the infinity. If this would have been less, then the your K factor would be either this or like for example, if 10, then it would be 2.28 like that. So this is the meaning of that. Once the K is defined, K equal to 2. In case of 95.45, K would be 2. If K is 2, then combined uncertainty will be multiplied by 2. Then this will give you 6.0259 multiplied by 2. It means, for example, the value is coming at 12.156 micron, like that. This will be the calculations will come out in that way. Now, here if you have anything to understand further, I'll just explain it again here. For once we get the combined uncertainty calculation with this, now this combined uncertainty of all the uncertainty, combined standard uncertainty, we need to convert into the overall uncertainty, measurement in uncertainty, or expanded uncertainty. To convert into that, all are the meaning is same. Either we say measurement uncertainty, measurement of uncertainty, overall uncertainty, expert uncertainty. All these are the 4 different terms, but meaning is same. They are talking about the same value. To convert the combined uncertainty into the overall uncertainty or expanded uncertainty, we need to multiply it with coverage factor. To get the coverage factor, we need to calculate the effective degree freedom. Once we calculate the effective degree freedom using this formula, if this value is coming out 30, then we have to consider the value, this value is this value is coming out 30. Then we need to, if considering the confidence level 95.45, then we need to multiply it with 2. If this value is not 30, maybe 10 or maybe for example 20, then in that case we need to multiply with 2.13. In our example, the value of the effective degree freedom is in millions, billions. Then that's why we're considering the 95.45 confidence level. Accordingly, we are using the K factor equal to 2. And that's why our value of the uncertainty or expanded uncertainty is coming out 12.156 by multiplying the K factor with the combined uncertainty. So this is what it is. I try to this is, though it's a very dry subject, to cover it in this span of time, 1.5 hour, 2 hours time. It's really a different task for all these things. I try to cover it. And now, if you have any questions, you can please ask me here. Any questions can be asked or anything about that? Ashutosh ji?
Thank you. Thank you very much, sir. Thank you for your kind and brief presentation. It was one of the best. And I am sharing your presentation with the calculation of measurement uncertainty with all the participants. It will be available on our website. This video will also be available on our website. The participants can see at any point of time wherever they need its help. I would like to thank, sir. Yeah.
Yeah, and certain questions, if you allow, then if
Yeah, please.
certain questions can be taken up from the either video of the people or the chat box, you suggest me.